Hello everyone, welcome to my virtual presentation. My name is Di Wan and I'm from the Norwegian University of Science and Technology. Today I'm going to present a work entitled Tensile and Fatigue Behavior of a Lead-Tin Antimony Alloy Investigated via Small-Scale In-Situ Mechanical Testing in an SEM. This is a joint work together with the NTNU, Nexans Norway, and Sintef Industry. Lead alloys are commonly used in subsea power cable sheathing due to its easy manufacturing, chemical stability, and relatively good mechanical ductility. A common understanding of this material is that it has a relatively low melting point, that is around 600 Kelvin or about 327 degrees C. This relatively low value made a lot of strange behaviors such as relaxation, recovery, recrystallization, and even creep happening already at room temperature in lead, in contrast to most conventional metallic materials which will experience these mechanisms only at high temperatures. These time-dependent phenomena will lead to a sensitive strain rate dependency of lead alloys in terms of the constitutive behavior and damage during deformation. However, the literature on lead is always limited and often very old. Therefore, we launched a comprehensive study to refresh the knowledge on lead via some advanced in-situ techniques with high resolution. The material used in this work is extruded from lead tubes with a storage time of more than 1 year. The chemical composition is shown as in this table. It's relatively pure lead with a small portion of both antimony and tin. We did an initial EBSD scan on the as received material. It can be seen that the grains are relatively homogeneous in well-annealed situation. The average grain size is about 22.6 micrometer, and the residual strain is relatively small. The average kernel average misorientation is only 0.37 degrees. The as-received material was further manufactured into dog bone-shaped tensile specimens according to this geometry, and the specimens are loaded in a small tensile compression module. This small machine is designed for in-situ tests in a scanning electron microscope. First, let's see an overview of the monotonic tensile deformation behavior. The specimen was directly loaded to necking followed by final fracture. The fracture was ductile without any unexpected brittle behavior. However, this magnification is not capable of observing local deformation behavior. So let's try with the higher magnification. At this magnification, we can see the deformation was not 100% homogeneous, but localized at some boundaries. The slip lines were mostly aligned in a direction that is perpendicular to the loading direction. The final fracture was overall straight and sharp, but locally in a zigzag-shaped sawtooth shape. After we have improved the surface quality and slowed down the strain rate, this becomes more obvious. Especially here you can see the deformation was accumulated along the boundaries, and even you can find some damages initiated from the boundaries. This slide shows the tensile properties of the tested lead alloy. A featured result is the strain rate dependency of this material throughout the whole tensile test. A faster strain rate will lead to a higher stress level. That's why we concluded different yielding strength and ultimate tensile strength values from the test with different initial strain rates. Another interesting fact is that if we change the strain rate during the test, the stress level will also change accordingly, such as this critical point and this critical point. When we change the strain rate from a -5 to -4, the stress level goes also a little bit higher, and these two curves meet each other. This is the same when we change from -4 to -3, then these two curves also meet each other. Based on the microstructure evolution, we have divided the tensile deformation into 3 stages. In the first stage, we see deformation accumulation along the grain boundaries, such as here, here, and here. The slip lines occur inside the grains with a single direction, such as this one, this one, this one, and this one. Some damages can occur at grain boundaries, such as this one, but no significant change close to these precipitate faces, like this. The second stage involves higher strain levels. The deformation accumulates more at grain boundaries and the damages become more significant, such as this area, and this area. The slip lines occur in different directions, such as these ones, and these ones. There is also a slight debonding effect that happens close to the precipitate faces, but not very significantly. The final stage continues until the final fracture. The grains start to rotate in order to accommodate the high strain levels, and the slip bands are aligned vertical to the loading directions, and the fracture follows the direction of these deformation bands. Though we saw damage at grain boundaries and precipitates, the final fracture did not happen there. We also did a cyclic loading test with displacement controlled mode at a strain amplitude of about ±1%. From the stress time responses, a softening behavior is clearly recorded. You can see the stress level is becoming lower until saturation. The in-situ investigation recorded the real-time microstructure evolution. The deformation was accumulated mainly at the grain boundaries. We can clearly see the deformation bands on the surface of the specimens, and as the cycles increase, you can see these bands are becoming better and better visible. As a short summary, we observed several different damage modes. In monotonic tension, we saw damage initiation at grain boundaries or at precipitates, but the final fracture happened along the deformation bands resulting from slipping. The final failure was also in a shearing mode following the local deformation traces here. In cyclic loading, the deformation accumulated at grain boundary areas and appeared as extrusion and intrusions on the specimen surface, like this. This can be one of the reasons leading to the final fatigue failure of this material. Nevertheless, this is only a preliminary work at the moment, and the outlook in this field is really positive. Since we see twin boundaries in this current lead alloy, the effect of either deformation twin or annealing twin could be very interesting. Another important mechanism would be the fatigue creep synergy. It's necessary to check the strain rate effect in the fatigue response of the material and investigate the possible room temperature creep deformation. By implementing advanced techniques such as EBSD, we might be also able to explore the dynamic recovery and recrystallization behavior, which can be the possible reasons to explain why the cables last long in the real applications. These have been well planned by the current authors, and hopefully we will be able to explore more after the COVID restrictions have been released. We have submitted a manuscript on the current topic together with this video. Please check more details in the paper if you are interested in this study. Thanks for watching.